Thank you for joining. I'm Mark Braverman, and this is a presentation for the paper on news operations for external information. This is joint work with Dor Minzer from MIT. So the overall subject of this paper and this talk is communication complexity. So two-party communication complexity, there is Alice, two parties, Alice and Bob. Alice gets an input X, Bob gets an input Y, and they would like to use a protocol to compute a function F. And the studies of the question, how efficiently can this be done? This is the overall goal. The communication cost of the protocol is the number of bits exchanged in the worst case. And the communication complexity of a function is the number of bits exchanged by the best protocol in the worst case. So we are trying to find the lowest cost protocol. And this is true of all definitions. So first you define a cost notion for a protocol, and then it gives rise to a complexity notions for function as the lowest cost solution. For distributional communication, we have a communication protocol, and there is a distribution mu now, and the expected communication cost of pi is the expected number of bits exchanged when x and y are distributed according to mu. And the communication complexity, now we can also talk about error, which is so we are allowed to make mistakes with respect to some small fraction of inputs under mu. So we are looking for a protocol that solves F, except with maybe a small fraction of inputs, and we are trying to minimize its communication cost. So that's the distributional communication complexity. And a major goal is to prove lower bounds against communication complexity, which usually many models, a large fraction of unconditional lower bounds stem from lower bounds on communication complexity, or at least from techniques for proving such lower bounds. A prominent example in this context is the function set disjointness and the related function set intersection. So we have Alice and Bob are given vectors of n bits, and they want to find out if there is a bit, if there is a coordinate in which both of them have a 1. So that's set disjointness. And set disjointness, I mean, it's not obvious how to analyze it, but it is comprised of simple 2-bit n functions. So a dream proof for disjointness, but also in general in many models of complexity theory, is to say, well, the only thing you can do really is you have a problem comprised of smaller pieces. The only thing you can do is solve the pieces one by one. So to solve F, you must solve each coordinate separately. Wouldn't it be awesome? To solve a coordinate, to compute a 2-bit end, you need 2 bits of communication. So you get some linear lower bound right there. So unfortunately, direct sum for communication is wrong. So a statement of this sort that you must solve each, if you have something composed of many coordinates, you have to solve them one by one, is untrue. And it's untrue in many models, and including this one. But it is true if you replace communication with information complexity, and that was one of the motivations for developing the notion of information complexity. So again, any complexity measure starts with a cost measure on protocol. So the information cost of a protocol is given by the amount of information it reveals. If you've seen Shannon information definitions such as mutual information, that's good. If not, the important thing to know is that there are mathematical definitions to formalize what I'm going to say next. So the internal information cost of the protocol, so this term is what Bob learns about Alice's input. So Bob knows Y, and it's what pi reveals about X. And this is what Alice learns. So, and the internal information complexity you are trying to minimize, or in fact, it's an infimum, but you're trying to minimize the amount of information revealed about the inputs to each other while correctly solving f, and that's information complexity. And it turns out that direct sum actually is true for information complexity, and it is a plausible way to get a lower bound for disjointness and actually a tight bound, including the constant in front of n. So disjointness does require linear communication, and you can figure out the exact constant in front of n using this this connection to information complexity. So if we get a useful tool that tensorizes, it allows us to compute communication complexity of direct sums of functions. It actually is the communication complexity of direct sums of functions. There is a theorem that says that the internal information complexity of f is actually the limit amortized. So this is called amortized communication. So you take many copies of f and you look at the per copy communication cost. So information is equal to amortized communication, which is this quantity. There was some hope that actually it's also true for communication, that amortized communication is equal to one-shot communication, which in this language is equivalent to information being equal to communication. Then you would have this relationship true for communication and you wouldn't need information complexity to begin with. But it turns out that this is false. So there is a beautiful result by Ganor, Kohl, and Raz that shows that there is a Boolean function that gives an exponential separation between internal information and communication. So there is a function such that to compute it, you only need to reveal k bits of information, which also means that if you have many, many copies, the per copy cost is only k, but the communication cost of one copy is exponential, it's like 2 to the k. And in fact, this is the largest gap possible. There is a matching upper bound that the gap can be at most exponential. So it's actually critical that in all of this discussion, it's epsilon error and not zero error. Epsilon can be sublinear, it can be subconstant. It can be something like 1 over m or even a little smaller, but it cannot be zero. So the zero error amortized communication is not as well understood. And we don't know if there is an analog for zero error protocols. So changing gears a little bit. So this is one quantity that we don't understand, the zero error version of amortized communication. So another quantity that we'll discuss a connection in a minute, but is that of external information. So recall that the communication cost of a protocol is number of bits exchanged. The internal information cost of a protocol is the amount of information learned from the conversation the players learn about each other's inputs. The external information cost of a protocol is this mutual information, which is the amount of information that an external observer learns from pi about Alice and Bob's inputs. So it's the mutual information between x and y and the protocol pi. And by extension, the external information complexity of a function is again trying to minimize this quantity over all possible protocols or sequences of protocols. We are trying to solve f, revealing as little as possible to an external observer. And again, this quantity is not as well understood as communication complexity and internal information complexity, even though it was defined actually historically before internal information complexity. And so, okay, so what does it capture? So what do we know about it? We know that it's actually sandwiched between communication complexity and internal information complexity. So the fact that you don't reveal to anyone more bits than you communicate is a fairly simple fact. It's also true that it requires proof, but that an external observer always learns more, at least as much as the players themselves about the inputs. So we didn't know how far can this separation be, and some basic properties like tensorizations, and so in general it's not as well understood. So our first result is actually extending the exponential separation between Ganor, Call, and Raz from communication versus internal information to external information versus internal information. In fact, we just showed that the same example from the paper works. It's just that the proof techniques need to be refined to work against the smaller quantity of external information complexity. And again, this is tight. It's even tight for communication complexity. So, and the proof idea is rectangles. So the GKR proof relies on bounding rectangle partitions. So basically showing that any large rectangle with respect to some measure is roughly balanced, has this roughly the same number of zeros and ones with respect to f, which immediately means that if you have a protocol that cuts your space into, so a protocol with c bits of communication creates at most 2 to the c rectangles. So those are pretty big rectangles. If they're pretty balanced, that means that you'll have a lot of error. And I'm oversimplifying because those techniques can be pretty elaborate, but that's the basic idea. And it doesn't immediately translate into external information, because an external information protocol can partition the space into many pieces. It's not limited in terms of communication, but you can actually build with the right definitions, you can basically get this proof to extend to external information complexity, and that's what we do. So we have new tools for external information that previously only worked for communication complexity. So let's talk in some more detail about zero-error protocols. So the no-prom is this version of zero-error protocols. So we say that pi is a zero-error protocol if for all x and y it works. It gives the correct answer, so it's not allowed to make mistakes. There's a promise version of that says that if there is a distribution mu and mu puts mass 0 on something, then you are allowed to make mistakes there. So that's a promise version of zero-error protocols. Under the no promise version, this protocol has to be correct even on inputs that never appear under mu. And a conjecture from about 10 years ago was that if you take amortized zero-error communication complexity, it's equal, perhaps up to a constant, to zero-error external information complexity. And so this conjecture, there were some reasons to believe in it. It's not just taking two quantities that we don't really understand, the zero-error amortized communication and external information, and saying, okay, maybe they're equal to each other. So there was some evidence in favor of it. So for one direction is actually true. It follows from known protocol compression techniques, and it's actually important in that it's true, but it's only true with external. So it wouldn't be true for internal. For internal, if you try to prove the less than or equal direction, you only get some error here. But with external, you actually get to error 0. So there one direction is known to be true. And for some cases, it's actually true almost magically. So for set intersection, for example, which is just the amortized and, so you take the 2-bit AND function, you amortize it, you get the set intersection. The conjecture actually holds precisely. So the external information cost of complexity of the 2-bit AND is log 2(3), whereas the internal one is 1.49. And it turns out that those exactly capture the zero error. So that's a result from the 90s, communication complexity of set intersection and vanishing error. So if you require the answer to always be 100% correct, you have to use something like 1.58n. But if you allow yourself an error of 1 over n to the 10, you suddenly are 1.49n. And this exactly corresponds to the external versus internal gap. So there were reasons to believe this conjecture to be true. But it actually turns out to be false. So an earlier work from about 5 years ago by Kolmaran, Spilke, and Yudaev showed that under the promise formulation, the conjecture is false. So note that under the promise formulation, it's easier to have low amortized communication complexity. So it's easier to falsify the conjecture. And today, in this paper, we actually show that the conjecture is false in general. And in some sense, there is a quadratic separation there. So specifically, we show that there is a Boolean function f, where there is a quadratic separation between amortized zero error communication and even a small error external information complexity. So the separation is quadratic, and actually with an epsilon here, it's actually tight. So we show that the external information complexity with some small error is actually at most quadratic in the amortized zero error communication. So, so with epsilon here and zero here, this relationship is tight. And as a corollary, if you actually insist on a zero here, you get there is no dependence whatsoever. So zero error external information complexity is not dominated by any function of the amortized zero error communication complexity. This could be a constant and this could be large. So the conjecture is false. And in fact, if you allow a small amount of error, then we also learn the tight relationship between external information complexity and amortized zero error communication, and it's a meaningful relationship. It's at most quadratic. And so let's, so in the remaining 3 minutes, let's see a proof overview on one slide. So a quadratic separation hints at using the gap between deterministic and non-deterministic communication complexity. And in fact, this is the first ingredient of the proof. The first ingredient is a function h, where there is a quadratic gap between non-deterministic and randomized communication complexity. We know that this gap can be at most quadratic. So the function is, we have a matrix, like an m by m square, and every entry in this square is an AND of a bit that Alice has and then a bit that Bob has. And the function asks whether there is an all zero row. There is a row of all zeros. So there is always a certificate of length at most m log m that proves that the answer, proves the answer. So even though it would take m squared communication to figure out the answer, if someone gives you this certificate, you can actually verify it only, it's a certificate of length m. So to convince someone that there is not a row of all zeros, you have to show a 1 in every row. So that's m log m bits. And to convince them that there is an all zero row, you just need to show them the all zero row. So the zero error certificate, there is always a zero error certificate of length m log m, but the external information complexity of this problem, in fact, even the internal information complexity of this problem is m squared. This is important. So this is one ingredient. A second ingredient is the exponential separation that we started with between internal and external information complexity, which is also both ingredients. If you want the tight theorem that we get, in some, it's not hard to see that you need both ingredients. So we start with a function we call hint, which has a huge separation between internal and external information complexity. So its internal information complexity is subpolynomial in M, and its external information complexity is more than M cubed. So this could be, we know that there is an exponential separation here. So there exists such a function. And we use this function to encode the hint to Alice and Bob. Okay, so we need to show two things: that the amortized zero error communication complexity is low and that the external information complexity is high. So to see that the amortized zero error communication is low, so we now have to solve many copies of this problem. So first, because it's many copies, the internal information complexity of f hint is low, when you have to solve many copies, you can do it with little communication. So at cost of c times something subpolynomial, you can actually compute the hint and extract the ci from the hint. So this will have errors, so that's not perfect, but you can actually extract the certificate. Then you can check the certificate using only c bits of communication and only accept if the certificate is valid. So you never accept anything that's wrong. So you never make a mistake. If you get an invalid certificate, you actually repeat the whole procedure. But the probability of that is very low. So we get very low expected communication. So the amortized communication cost is c times something subpolynomial of m. So it's essentially linear in m. So that's one direction. And in the opposite direction, so the external information cost, so the hint is essentially useless, because even to extract one bit of C, you need at least m cubed external information cost. So essentially, using external information cost of m squared, you can't get anything useful out of the hint. So without using the hint, you're stuck with this first problem, and so the external information cost is m squared. And that concludes the sketch of the proof. So it's a bit convoluted, but it has to be convoluted because, for example, if there was no separation between internal information complexity and communication complexity, this example couldn't exist. So it's quite delicate for a reason. So this leaves us with a major open problem of actually understanding. So remember, there were two quantities we didn't understand: zero error amortized communication and external information complexity. We understand external information complexity a little better as the result of this work, but this leaves us with not understanding this limit at all. So what is it? It's in the language of information theory, what's the single letter characterization of this? But basically understand this quantity. How does the zero error communication complexity of F scales with many copies? So if you allow even a tiny amount of error, like 1 over m, it becomes an internal information complexity. But with zero, we don't know what it is. So thank you. And I'm looking forward to the conference. Thank you.